Page 52, solving multi-step equations. So let's start out with an algorithm, just a set of steps to follow. The first thing we're going to do is, if we can and if we need to, we'll simplify expressions on each side of the equation. That includes combining like terms. Once we have those simplified, we're going to get all variable terms on one side and all constants, so numbers without variables, on the other side. And whatever you do to one side of the equation, you also do to the other side of the equation. You must also do to the other side of the equation. So that's very important. And we'll see some examples shortly. Once we have all the variables on one side, we're going to isolate the variable. We're going to get it by itself using the inverse or kind of opposite operations to undo the equation. Isolate means to solve for the variable or to get it all by itself with a coefficient of 1 on one side of the equation. So we have x equals, and then we have a bunch of stuff on the right maybe, but none of it involves x's. Finally, this is really important. We want to check the solution by substituting the value of the variable back into the equation. We want to make sure that's true. So basically plug it back in and check your work. Okay, let's start out. Example 1, we have 12.5 minus x equals negative 7.5. And we have several options here. We can move this constant over, we can move this x over, we can move this constant over. We're going to ask ourselves, what does it make the most sense to do in this case? Well, I can't simplify either side, so I'm done with step 1. Step 2 says, let's get all the variables on one side, all the constants on the other. Right now I have a variable over here and 2 constants, one on each side. So I'm going to move this constant over here. And to do that, I'm going to do the same thing to both sides. I'm going to subtract 12.5, do the opposite of it. When I do that, I get 0 minus x, or just negative x, equals negative 7.5 and minus 12.5. I'm taking a negative, I'm subtracting, so I'm making it even smaller. Basically, I'm adding these two, negative 7.5 and negative 12.5. Add them up, I get negative 20. Remember, they're both negative, so that means that their sum is going to be negative. Negative x is negative 20, okay, that's almost x by itself. I want a 1 here, so I'm going to multiply by negative 1, or divide by negative 1. They're equivalent. And then I get x equals 20. Now we're not quite done, because remember we have to check to substitute the value in. So let's do our check. I like to do this step in a different color, just to keep things straight. So I have 12.5 minus x equals negative 7.5. I have the original equation. 12.5 minus, we're saying x is 20, so let's plug in 20 here, equals negative 7.5, I hope. Great. This is, if it works out, we've checked our solution. 12.5 minus 20, so I'm subtracting a bigger number from a smaller number. It's going to give me something negative. That's a good sign. And 20 minus 12.5 is 7.5. So we have negative 7.5 equals negative 7.5. It checks out. If you get the same thing on both sides, whether it's negative 7.5 equals negative 7.5 or 0 equals 0 or what have you, you've checked your solution. And if you get something different, either the check has a mistake in it or the original problem, or possibly both. Okay, let's take a look at another example. Example 2. Okay, so we have negative 7/2 equals x over 10. Negative 7/2 equals x over 10. I need to do the same thing to both sides to get x by itself. I have several options here. The one that I would do in this case is multiply by the thing we're dividing by, multiply by the denominator. Multiply both sides by 10 and see what happens. I'll give you a moment to pause it if you'd like. Solve this one. And we'll take a look at example 3, which we'll do together. 1/4 y minus 2. Make sure your 4's and your y's look very different. Equals 3. Okay. 1/4 y minus 2 equals 3. We basically want to do the opposite of order of operations. So we're going to start with adding and subtracting. There's nothing to simplify, so we start with adding and subtracting. I want to get rid of this minus 2 because that's added or subtracted to my variable. I'll worry about the multiplication later. So how do I get rid of minus 2? Well, I add 2 to it. Have to do it to both sides. So I get 1/4 y minus 2 and plus 2 cancel out equals 5. No adding or subtracting going on, so I can move on to multiplying and dividing. This is multiplied by 1/4. So I can either divide by 1/4 or equivalently multiply by the reciprocal. So multiply by the reciprocal, I'm going to get something times 4/1, and 4/1 is just 4. I wrote it 2 different ways, but I'm really doing the same thing. I get y equals 20. I guess we liked 20 when we wrote these examples. Okay, so y equals 20. Let's check it. Maybe we made a mistake. One-fourth of 20 minus 2 equals 3, I hope. 1/4 of 20, that's 20 over 4, so that's 5. 5 minus 2, yep, that's 3. It checks out. Let's get number 4 on here too. Number 4, we're actually going to have to simplify a little bit. Okay, so example 4 is 3x plus 4 plus 5x plus 7, yes, 7 equals 88 plus x. So far we haven't had to do step 1 of combining like terms. Now we do. Now we have like terms. And technically we actually can do this a couple different ways. So let's see 2 ways to do this. The first way is I'm going to combine like terms. I notice that 3x plus 5x can be combined. I notice that plus 4 and plus 7 can be combined. And over here, there's really not much to do. So I can turn that into 8x plus 11 equals 88 plus x. Let's do that a different way, though. What if I took 3x plus 4 plus 5x plus 7 equals 88 plus x and said, I think I'm going to get rid of that plus x over there. That's kind of bothering me. Move all my x's to the left. You can do that. Subtract x. Subtract x. Now, one common mistake, do not write down what I'm about to do, is to subtract x from every place. But then I'm doing it twice on the left and only once on the right. I need to decide one of these. And it can be either one, because whether I subtract it from the 3x or subtract it from the 5x, in the end, we're decreasing it by x. So probably shouldn't have written that at all, but 3x minus x, it's not 3, it's 2x, because we're subtracting an x. We have 3 of them, we're subtracting 1, we get 2x, plus 4, plus 5x, plus 7 equals 88. And now that plus x is gone. Okay, that's good. Maybe I want to get rid of that 7 next. I can combine like terms like I did over here, or I can just subtract it from both sides. And either option is completely valid. We're going to get the same answer either way, as we'll see. So now I have 2x plus 4 plus 5x equals 81. Okay, let's get rid of that 4. Let's move all the variables over here and all the constants over there. So subtract 4 from both sides. I get 2x plus 5x equals 77. Well, I told you you were going to get the same answer, but we're not done yet, right? 8x plus 11 equals 88 plus x. Let's take that one step further. So I'm taking method 1. Let's see, we'll call it method A so that it doesn't get confused with example 1. And here's method B. Method A, I have 8x plus 11 is 88 plus x. I'm going to, I generally like the x's on the left. I'll subtract away an x from both sides. Again, remembering that's not 8, that's 7x. 7x plus 11 equals 88. Subtract 11 from both sides. 7x equals 77. Looks familiar. Because this is about to be 7x equals 77. We've gotten to the same place through 2 very different methods. And once we have 7x equals 77, we almost have what x equals. I just have to do the opposite of multiplying by 7. I have to divide by 7. And I get x equals 11. I'll go ahead and leave that to you to check, but I want to make sure that when you check the x equals 11, you don't just check it in kind of the most recent equation. You go back up to the very top. Oh, not that far. 3x plus 4 plus 5x plus 7 is 88 plus x. And you plug in, what did we just find? 11. You plug in 11 for each of these x's, all 3 of these x's, and then you evaluate, and it does work out. Okay. Let's look at example 5. So we have negative 20y plus 15 equals 2 minus 16y plus 11. You can stop it here and think about what you want to do. Or if you have already thought about it and just want to check, or if you aren't quite sure, I'd start by combining like terms. Again, you can instead subtract away the 2 from both sides or subtract away the 11 from both sides. Just make sure when you do it that you only do it once from this side, once from this side. Then you're going to get your your y terms over here, your numbers over there, or it could be the other way. When you're done, you will get a fraction, not a terrible fraction though. Go ahead and plug that fraction in here and here. Here and here, and check to make sure that it works out. Okay. Example 6. We have 3a minus 11 halves equals negative 3a over 2 plus 25 over 2. Lots of fractions. So fractions aren't terrible, but I'd rather work with whole numbers when I can, or integers rather. So let's do that. I can do pretty much whatever I want to the left side of the equation as long as I also do it to the right, and vice versa. So what if these are all divided by 2? Let's multiply by 2, every single term. So this is just times 2. This is, I think of it as 2 over 1, 2 over 1, 2 over 1. I have to multiply every single term by that 2 over 1. And when I do, I get 6a minus 11 equals negative 3a plus 25. And I think you can take it from there. Again, go ahead and figure out what this is and substitute it back in to check your answer. Example 7, we have 4 times 2a plus 3, so this looks a little different, equals negative 3a minus 1 plus 31. So now we've got something that looks like distributing here. Looks like it's distributing because it is distributing, right? Let's distribute the 4 to the 2a and the 3. Distribute the minus 3 to the a and the minus 1. Watch your signs, and then you can start simplifying and combining like terms and so on. 8. As always, feel free to pause and do those now, or do them when you're done with the video. Okay, 1/2 x minus 3 equals 2 minus 3/4 x. I would do basically the same thing I did up here. I'd clear the denominators, but the difference is that I would use a denominator of 4 in this case. Why 4? Think about it a moment. Basically, 4 is the least common multiple of all the denominators. It's the smallest number that every denominator goes into, which guarantees that it's going to cancel out all of these fractions, leaving them as integers. So I'll leave this one for you to do, and I'll give you a hint. Try it out multiplying by 4. You can do it other ways, but I'd like you to at least give that a try. Remember when you multiply to multiply the 3 and the 2 by 4 as well, the whole numbers and the fractional terms. Example 9, 1/2 times 2 plus a equals 3a plus 4 over 3 squared. Okay, we've got to do some work here. I'm going to start by getting rid of my fractions again. I've got a 2 in the denominator, I've got a 3 squared in the denominator, so that's a 9. The least common multiple of 2 and 9, the smallest number that they both go into, is 18. So I'm going to multiply by 18. Times 18 over 1 times 18 over 1. Notice that I do not multiply inside and outside. This is in parentheses, so this 18 applies to the 2 and to the a. I don't need to multiply it by the inside as well. It's already taken care of by doing this. Similarly, the 18, I don't need to multiply it by the 3 and the 4 if I just think of it as being a set. Remember we said fraction bars can be grouping symbols. Okay, so 18 over 1 times 1 over 2, that's 9, times 2 plus a equals, this was a 9, so turn that into a 2. We have 3a plus 4 times 2. Distribute. Notice that they look a little different. We've got the single term on the right. That's okay. You can still distribute. If you like to draw your little arcs, you can do it that way. And then run through it. As always, remember to check your work. This is something that we'll be using a lot. So we've got a lot of examples here. 1/3 minus 2y over 9 equals 19. Again, I would recommend multiplying by the least common multiple of 3 and 9. 11, let's look at some decimals. It's a little different. 0.4x, or 4/10 x, minus 0.25, or 25 hundredths, equals 1.75. Okay, so just like fractions, I can work with decimals. But if I don't have to, if I can work with integers instead, I'd rather do that. So what can we multiply by to make these all into integers? Well, it's going to be, if I multiply by 10, that's taken care of. But I've got 2 decimal places here and 2 decimal places here. I'm going to multiply by 10 squared, by 100, to scoot every decimal point over 2 places. So this is times 100, this is times 100, this is times 100. That kind of looks like I'm taking it to the 100th power. Definitely not doing that. Okay. So 100 times 0.4x. I take the decimal point, I scoot it over 2 places because I'm multiplying by 100. I can't put it over the x, but I can remember that 0.4 is the same as 0.40. So scoot that over twice, I have 40x. 40x. 4/10 is the same as 40 hundredths, right? This is like 40 cents. 40x minus, scoot this over twice. I get just plain 25. Equals, scoot this over twice. 175. Now, I have all integers. 40x minus 25 is 175. Again, these are not like terms, so I can't just combine those. But what I can do is I can move this 25, this constant term, get it on the other side. Ask yourself, how do you do that? What can we do? Well, we can add 25 to both sides. That makes up for subtracting 25 away. Now we have 40x equals 200. Got some nice whole numbers. I'm going to divide. I happen to notice that 40 goes into 200. I could take out a 10 on each side first and then have 4 and 20, or I can divide the whole thing by 40 right off the bat. I get x equals 5. As always, we want to check our work, and we do want to check work in the original equation, the one with all the messy decimals. But basically what you can think of doing when we multiply by 100 or by anything In this case, we're kind of turning it from dollars into cents, right? If you have $1.75, you have 175 pennies. We're just changing our units, really. Multiplying it by 1 followed by however many zeros there are on the number with the most decimal digits after the decimal point. So let's look at one more example like that. We'll just start it out. If I have 7.3 C minus 5.048 equals 16. I do not want you to solve this one. This is not going to work out nicely. But what I see is that the number with the most digits after the decimal point is this one. It's got 1, 2, 3. So I need to scoot the decimal point over, which is here, 3 places. I need to scoot it over here 1, 2, 3 places. So I end up with 7,300 C minus 5,048 equals 16,000, and that is a comma, not a decimal point. So now I have all whole numbers, and then I could work from there. Again, you do not have to do this example unless you're really keen on it, because it's probably going to be really, really messy. We could do it, but let's not. Oops. Okay, last example for now. 13, we have 1/4 times A plus 3 equals 2 minus A. This one actually works out pretty nicely. I'll let you solve that, and I'll see you in the next video.